Welcome to my YouTube channel, friends. This is Ricky Chisambo, and in this lesson we want to revise science paper 1, which was written in 2020. So the duration for this paper was 2 hours. So you can read through the instructions. Okay, so we'll start with section A. So section A, you have to answer all the questions. So A1, how many significant figures are in 2.0800? So the significant figures you have to count because there is a point here. So the whole number and the decimal numbers, you have to count them as well. So when you count them, 1, which is 2, so 1, 2, 3, 4, and 5 there. So the answer is 5. And then, which of the following contains base physical quantities only? So physical quantities only is what we are looking at. So length in kilometers, mass in tons. So this is incorrect. Number B, length in meters, mass in tons. Still it is not convincing. C, length in kilometers, mass in kilograms. So still it is not convincing. So let us look at D, length in meters, mass in kilograms. So this is convincing and this is the answer. Okay, so let us move. So the following diagrams show steps that a learner carried out in order to determine the volume of a wooden cork. So we have the diagrams here. So step 1, you can see here step 1, and then we have step 2, and then we have step 3. So what was happening here is we have a glass bulb. So a glass bulb was dipped in, and then the liquid had to increase from 50. So this is 10, 20, so 30, 40, and then this is 50. So the volume for this liquid is 50. So 50, that is the volume. And then, so this glass bulb was dipped in the liquid, and then the liquid had to increase from 50 to what? To 60. So this is 50. So from 50 to 60. So meaning that the difference here is 10. So that is the difference. So that is the difference. Let us look at the other one. Here it has increased. So from 60 to 100. So here we have 70, and then here we have 90 there. So from 60 to 100. So meaning that 100 minus 60, what are we going to have? So we're going to have 40 there. So that is an increment there. So now let us go and see the question. So which one is the volume of the wooden cork? So the wooden cork, this is the wooden cork. So this is the wooden cork. This is what we want, the volume for the wooden cork. So remember, this glass bulb is, or it has a volume of 10. And then, so identical, so they were the same. So meaning that if this is 10, and then this is also what? 10. So how do we find? So we can say 100 minus 50. So we're going to have a 50 there. So now this 50, it is we've removed the first volume of the liquid. So we're going to remain with a 50. So in this 50 that we're going to remain with, so this 50 that we're going to remain with, we're going to subtract 20 for what? For these identical corks. So which is the one the one at the bottom, it is 10, and the one on top, it is 10. So 10 plus 10, it is 20. So if we subtract, we're going to get 30 there. So meaning that the answer here, it is A. Okay, we can move. 4. Which of the following diagrams show an accelerating car? So we have a car which was accelerating. So when we look at the first one, it is distance against what? Time. Then distance against time, distance against time. So I want to explain something before we answer the question. So you find that the time graph, let me draw a time graph here. So we're going to give this to be as an example. So meaning that here when we say this is distance, and then here we are going to say that is what? Time. So if we say a car accelerates, so meaning that it is increasing in distance and what? And time. So here you find that here at x, the distance is constant, and then it is just increasing in what? In time. So here you find that it will start to deaccelerate, meaning that it will start to reduce. It is coming to where? To rest. So because we are looking at the acceleration now, this is not what we have here. So what we have here is number one, this let me say A. So we have A. So this is distance against time. So meaning that when you look at the car, it's coming from rest, which is 0, and then it is going this direction. So it is increasing, number one, in what? In time, and then not only time but also what? Distance. So this is acceleration. And then the other one, we are saying that it will start to increase in distance, but also it will start to it will undergo retardation, because there is that constant in time when we look at here. And then the other one, which is here, we are saying that the distance is what? Is constant. So it is moving in single direction, and then it is only increasing by what? By time. And then this one also, it is the same explanation that we've given in for example, in this diagram that I drew here. So now what is the answer here? So which of the following diagrams shows an accelerating car? So an accelerating car. So from what we've explained, the answer here, it is what? It is B. Okay, so the diagram below shows a light bar PR pivoted at P, balanced by a 4 Newton weight and force F. So we have force, so this is force. So we are saying that this is force. And then what else do we have? So this is the pivot here. So we have a pivot there. So that is where we find the pivot. Now, for us to understand what we are talking about, this question came from moment. So you'd find that in this question, you'd find that we have force and weight. So we have force and weight. So these two, force and weight, in this question, they are equal. So they are equal because they are balanced. So when you look at the diagram here, the weight and the force. So meaning that this bar is balanced. So now, it is very important that we understand and we find, we calculate so that it can be very easy for us to answer the question which has been given to say, what is the reading on the Newton balance? So we want to know. So the formula that we can use here, because we're looking at force, so we'll say F1 times D1. So this is force, and then we have distance 1, so is equal to force 2 times distance, which is what? Which is 2 again. So now let us identify from the diagram here. So which one is force? So the first one is this one. So this is F. So what will be force 1? And then let us look at the distance. So the distance that we are looking at here is what? So this is distance 1. So which is 30 from here to there. So the distance there is 30. And then force 2 is what we are looking for. And then here we're going to find the distance 2 for the balance of this diagram. So meaning that we're going to do, for us to have distance 2, we're going to add 30 plus 20. So we're going to have a 50 there. So meaning that we can substitute. So we are saying that F1, so F1 is 4 times 30 is equal to F2 times 50. So when you multiply, you'd find that 4 times 30, what do we have? So 4 times 30, we have 120. So here we have 120 is equal to, so we have 50 F2. So now for F2 to be solved, we have to introduce a 50 here, and then we introduce a 50 there as well, and then 50 goes. So we have F2 is equal to, so 0 goes, so 12 divide 5, what do we have? So we have 2.4, that is in newtons. So now let us move and go back to what we are looking for. So do we have that answer? Yes. So the answer here, it is what? It is B. So we can move. So a car is traveling on a level road. Suddenly the driver of the car sees a cow crossing the road and decides to apply brakes. What are the energy changes as the car slows down? So there are certain things that we have to understand here. So a car is traveling on a level road. So the car was moving. And then the other thing, suddenly the driver sees a cow crossing the road and decides to apply what? To apply brakes. What are the energy changes as? So the first one here, the energy is chemical to kinetic energy and sound. So this is incorrect. So kinetic heat to kinetic and sound. So this is also not convincing. It is not correct. So we have kinetic to mechanical and sound, as well as this one is not convincing. So the answer is D. So we are saying that we have, because the car was in motion, so it was possessing kinetic energy. Now when the brakes was applied, you'd find that because of the friction, so that friction between the tar and the rod, there was that production of heat. So once heat has been produced, and then you'd find that also sound would do what? Will be produced. So the answer is D. So let us move to question 7. So the graph below shows a cooling curve of a gaseous substance. So this is, we have the energy. So we have the energy, and then we have what? Time. So now, for us to understand the question here, it is very, very important that we pay much attention to it. In which states of matter will the substance be between points F and D? So we have to know the states of what? The states of matter. So the states of matter, we're saying that the first one, it is gas, and then we have liquid, and then we have solid. So now, because we have energy, so meaning that energy from E to F, so from E to F, this state here, this state is, we're going to say, this is gaseous what? Gaseous state. So that is gas there. So when you look, there is loss of energy. So loss of what? Of energy. And then here you'd find that from F to G, so from F to G, it has changed from gas now into what? Into from gas to liquid. So from gas to liquid. So from gas to liquid. Now there is no loss of what? Of energy here, because it is constant from F to G. And then we have G to H. So G to H, you'd find that there will be loss of what? Loss of energy. So meaning that if there is loss of energy, you'd find that here we are going to have, this is still from G to H. From G to H, it is liquid still. So this is liquid. But there will be loss of what? Loss of energy. And then we have H to I. So H to I, the state will be solid. The state will be what? Solid. So here the state will be solid. So meaning that it will be from liquid to solid. So now the question, in which states of matter will the substance between point F and G? So point F and G. So point F and G. So what is the answer here? So the answer is gas and liquid. So that is the answer. The following diagram shows a water wave. So this is a water wave. Now it is very important for us to understand what we mean when we say a wave. So meaning that we have this. So we're going to draw there. So we'll say it is looking like this. So let us identify certain things. So the distance from, so this is the crest. And then we have the distance here. So this is the amplitude. So this is the amplitude. And then we have, this is the trough. And then what else do we have that we have to understand? So this is the equilibrium. So meaning that it is the balance. So it is the equilibrium, or you can say it is the balance. So now, according to the question, you'd find that here we have this distance. So this distance, it is what? 8.0 centimeters. And then when we move, so meaning that this is what? Is 5 centimeters. So which row gives the correct value for the wave amplitude and the wavelength? So amplitude and wavelength. So we have 4, which is the amplitude. So 4, which is the amplitude, and then the wavelength is 10. Okay, so we can move. We have B4, which is the amplitude, and then 5, which is the wavelength. 8, which it is 5, and then we have 8, and then we have what? 10. So here, when we look very carefully, according to what we've explained, we are saying that the amplitude, so the amplitude, which is what? Here, the amplitude is what? So here the amplitude is 4. Again, here you'd find that we have 4 as well. So 4 plus 4, we're going to have 8. So this is the 8 that we have here. And then what else? So we are saying that the other thing, the wavelength. So the wavelength, so for us to have the wavelength, which should be complete, so we are saying that from here to here it is 5 centimeters. So same applies with from here to here it is 5 centimeters. So for us to have a complete one, we're going to have 5 plus 5, and then we are going to have a 10. So a 10, it is the wavelength. So the answer here that we have is A. Okay, so we can move. The diagram below shows a learner in front of a loudspeaker that produces sound. So this is a loudspeaker, it is producing what? Sound. So we have a mirror here. So this is the classroom wall. So this is the classroom wall, and then we have the loudspeaker there. So this is, just imagine this is you now. So which of the following diagrams best shows how the gaseous air molecules between the learner and the loudspeakers will move? So we want to know how the molecules will move from the speaker to the ear of a learner. So we would say, number one, what we have to understand is that sound, so sound is a longitudinal. So it is a longitudinal wave. So it is a longitudinal wave. So meaning that it will be moving in this this direction. So now the particles here, so these are particles. So meaning that the particles will do what? Will be vibrating. So as the particles are vibrating, there will be this collision between the particles. So meaning that once they collide going this direction, also they will move back to this direction, because particles, they will not move. So they will not move, but they will just what? Vibrate. So they will just vibrate. So when we look at the answers that have been given, so here, so these are particles. So meaning that they are moving in this direction. So they are vibrating in this direction. And then also they are coming to the position. So the answer that we have, which is complete, it is A. Let us go to question 10. So question 10. A girl of height 1.2 meters stands 4.0 meters in front of a plane mirror, as shown in the diagram, as shown in the following diagram. So this is a learner or a girl who was standing 4 meters away from the mirror. So the height of this lady or this girl is 1.2 meters. And then this is the ground, and then this is the mirror. So we have the ground and we have the mirror there. Now, what we have to understand is this. So this is the object. So this is the object. So in the mirror, because we have a mirror, obviously we should have an image. So where can we find the image? So the image is found behind the what? The mirror. So meaning that we're going to say, so because the person will be found, or the image, so this is the image, we'll say image. So the image is behind the mirror. So would say, so we have, that is the distance. So the girl, okay. So the height is the same. Don't mind about the drawing. So the height is what? Is the same, which is 1.2 meters. And then here you'd find that we're going to have 4.0 meters. So now what can prove this? So what can prove this is that to find the distance, you'd say, so distance is equal to, or we use this space, so distance is equal to distance of the object, so distance of the object plus distance of the image. So that is what we're going to have. So meaning that D will be, so distance is 4. So this distance is 4. And then also the distance here is what? Is 4. So 4 plus 4, it is 8. So that is the distance that we have. So when we go to the answers, do we have 8? So the answer is D. A line JK drawn on a piece of plain paper on which a glass block is placed was viewed through the top, and its image was located using a pin as shown in the following diagram. So we have an eye here, and then the line we have JK. So this is the line JK. This is the line JK. And then we have, this is a glass block, and then we have a pin which is at L, locating pin. So now what is the question? So if KL, so if KL, so KL is 1.8, KM, so KM, so KM, so would say KM, so KM is what? Is 4.8 centimeters. And here we had centimeters. What is the reflective index of the glass? So we want to find the reflective index of what? Of the glass. Okay, so we are saying that for us to find the reflective index of the glass, we have to know the what? The real depth. So the real depth. So if we've been given, we want to identify and to know the real what? The real depth. So we would say, let us write the formula that we're going to use. So reflective index. So reflective index is equal to real depth over apparent, so apparent depth, apparent depth. So what is the real depth? What is the real depth? So KL, so KM, so KM, that is the real what of this glass block. So it is 4.8. So we'd say 4.8. And then let us look at the apparent depth. So the apparent depth, how do we find this apparent depth? So we'd say, because we have this distance that we've been given, K to L, it is 1.8. And then we have the apparent what? We have the real depth. So we'd say 4.8 minus this one which we've been given, KL, which is 1.8 centimeters. So when we subtract, we're going to have a 3. So this 3 that we have, it is the apparent what? Depth. So that is 3. And then when we calculate on our calculator, we're going to have 1.6. So the answer here, it is 1.6, so which is C. We can move. So which of the following material would be most suitable for constructing a core of an electromagnet? So the answer here, the answer, carbon, no, it is not a magnetic material. Copper, it is not a magnetic material. So we have iron and what? And steel. So these are two magnetic materials that we have here. So meaning that because we want to make electromagnetic material, so the answer here, it is C. Now why do we find C to be the answer? So we are saying that iron, it is a soft, so this is a soft metal. So it is easy to magnetize it. So it is easy to magnetize it, and it is easy to do what? To demagnetize. So it is easy to magnetize and demagnetize it. So the answer here, it is what? It is iron, which is C. Let us move. So two unchanged metal spheres, so we have Q and P, are placed on insulating stands and are separated, while the negatively charged polythene strip is laid near Q as shown in the diagram. So we have negatively charged polythene strip. So this is polythene strip. So it is negatively charged. So we have these negatives that we can see here. So we have these negatives. So meaning that it is negatively charged. And then we have these spheres. So these spheres are metals which are uncharged. So because these spheres are uncharged, so you'd find that this will be attracted to this metal here. So now this metal, it has particles. So these are charged. So it is also, these are charged, but we cannot see. So we have, so let me write here. So here we are saying that it is, or it comprises of what? So we have positive and what? And negative. Then positive and also what? Negative there. So meaning that if it comes in contact with the negatively charged strip, meaning that the negatives here, the negative will move, and then the positive will do what? Will move. So in this case, you'd find that here we're going to have the positives here, and then the negatives will move where? So it will move in this direction. So let us see how the question is. So we are saying, what would be the charges on Q and P? So the charges on Q and what? And P. So the charges on Q and P, it is, so we're explaining, so that is positive and then the negative. Let us move to question 14. The following diagram shows the network of 3 resistors. So we have resistor 1, so we have resistor 1 here, and then we have resistor 2 here, then we have resistor 3 here as well, connected to a battery. So we have a voltmeter, so we have 1, and then we have 2 here, and then the last one, which is 3 here, are connected to R1, R2, and R3 respectively. So which of the following expressions show the potential difference? So the potential difference, which is PD, supplied by the battery. So we want to see the potential difference. So we are saying that the potential difference in this case, the potential difference we would say, potential difference is, would say voltmeter 1 plus voltmeter 2, or you can say voltmeter 1 plus voltmeter 3 there. So now, because these are parallel, so they are parallel to each other. So we can look at the questions that we've been the question and the answers. So which of the following expression shows the potential difference supplied by the battery? So the battery, how it was supplying the potential difference. So here we have the answer, which is A. So as you can see, so we have this. Okay, so we can move. So an electric kettle is rated. So we have electrical kettle, which is 230 volts, and then we have 3000 watts. What is the suitable fuse to use on this kettle? So a fuse, when we talk about a fuse, what comes on our mind? So we are saying that a fuse, this fuse, it allows, so a fuse allows current, so current to pass through it, so to pass through it. So we can say, because it allows fuse, or it allows current to pass through it, so we can say, because we're looking at now, we want to look at power. So we would say power is equal to, so we have current, so we have current there, so current times what? Voltage. So current times voltage. So we are saying that P, which is power, so we would say current, so this is current, and then we have V there. So now how do we calculate? What are we looking for here? What are we looking for here? So we want to find the current. So we want to find the current which passed through the what? The fuse. So we would say power. So power, we've been given power, and we've been given what? Voltage there. So we can say, okay, so we can say power 3000. So 3000 is equal to, so we have current, which is, so current, which is 230 voltage, we have voltage, so current we don't have. And then what are we going to do here? So we are going to divide 330, and then here we divide 230. So this will go, so we're going to have this is equal to, so this will go and then that will go, so 300. So 300 when we divide 23, what are we going to have? So we are going to have 13. So we're going to have 13, and then now here we're going to find which one is the nearest. So we're going to go to, so the nearest is D, which is 15. We found what current is. So let us move. So below are 3 statements on electromagnetism. So we have 3 statements on electromagnetism. So the first one is an electromagnet consists of a core of wire wound on a soft iron core. So this one, we move to the other one. So the strength of the magnetic field produced by an electromagnet increases if the strength of the current or the number of turns on the wire is increased. And then in the diagram below, when the switch is closed, the gap R increases. So the gap R increases. So we have the diagram here. So this is a magnet, and then this is we have south pole, and then we have the north pole there, and then we have the R. So this is the electromagnet that we have here. So now there are certain things that we have to do that we have to understand here. So you would find that they are telling us to say which of the above statements are true. So which of the above statements are true. So here you find that an electromagnet consists of a core of wire wood on a soft core, which a soft iron core. So this one, which is what? So this is correct. So this is correct. And then the strength of the magnetic field produced by an electromagnet increases if the strength of the current and the number of turns. So once you increase the number of turns, it means that you're going to also increase the strength of the magnet that will be produced here, which is also correct. And then the diagram below, which is showing when the switch is closed, the gap R increases. So R increases. So this R will do what? It will increase. So this it is not correct. So let us move to the answers. So which of the above statements are true? So we have, so the answer here, it is A, 1 and 2 are the statements which are correct. So let us move to question 17. So the diagram below shows a filament lamp rated. So we have 6 volts connected to the output of a transformer. So we have, so it is connected to the output. So this is, so this side, it is the input. So this is the input, and then here it is the output. So now this filament lamp was connected to the output. So we have the number of turns, and here we have the number of turns, and then we have the voltage here. Now how do we find this? How do we find the answer for this question? How do we find the answer for this question? So you'd find that it is very important that we know, here we don't know the voltage, but we know the number of turns. So here we know the number of turns, and then we know the number of what? Voltage. We know the voltage that we've been given here. So let us find the voltage. So this is the primary. So this is the primary, and this is what? The secondary. So the formula that we can find, the formula that will help us to find the difference here, it is, would say, voltage on the secondary coil over voltage on the primary is equal to number of turns on the secondary over number of turns on the primary. So we're going to substitute. So we're going to substitute number here, secondary, here, the secondary we don't have. So here we don't have, and then here we have on the primary. So we'd say V over, so on the primary, what is the voltage? So we have 240, and then is equal to number of turns on the secondary. So we have 20 over number of turns 300. So when you reach here, you're going to cross multiply, and then we're going to have 3 is equal to, so when you multiply 20, so when you multiply 20 times 240, so what do we have? So we have 4,800. So over 300, here over 300, then there, so V is equal to, so we can divide 300. So the answer that we're going to have is 16. So we're going to have 16. So this 16, this is 16 what? 16 volts. So now this 16 volts that we have here, so it is 16 what? 16 volts that we have here. Now what will happen to this filament? Because we have that. So what will happen to this filament? Let us look at the answers. So you find that the answer A, lights dimly, does not light at all. C, lights at normal brightness. D, lights up brightly and then blows off. So the answer here, it is D, because there will be too much voltage here. There will be too much voltage here, such that the filament lamp cannot contain the voltage which will be produced. So therefore the light will it will light brightly, yes, but this filament will do what? Will blow off. So the answer, it is D there. So we can move. 18. Which component used in electronic current circuits allow current to flow through in one direction only? So the answer is diode. So when you look at it, the resistor, thermistor, and then we have the transformer. So the answer is there. Let us move to 19. An atom of uranium, so 235 has 92 electrons. How many protons are there in one atom of uranium? So we have uranium here. So this uranium that we have here, they've asked us to say how many protons are there in one atom of uranium, which is 235. So the answer here, it is very simple. So the answer is A. So when we write, so we have the uranium. So the electrons that we're going to have is 92. Let's move to question 20. So we are saying that a radioactivity material gave a count rate of 8,000 counts per minute. After 20 days, it gives a count rate of 500 counts per minute. what is the half-life of the material? So we want to find the half-life of the material which has been given here. So you'll find that we have 8,000 counts, and then when we say it undergoes a decay, you'll find that half-life of this is 400, and then the half of 4,000, the half of 4,000. What is the half of 4,000? So we are saying that the half of 4,000 is 2,000, and then the half of 2,000. So we are saying that the half of 2,000. So the half of 2,000 is 1,000. The half of 1,000 is what? Is 500. So when you look at here, this is the period where it took how many days? So it took, so we have these days. So we are saying that the counts, a radioactivity material gives a count rate of 8,000 counts per minute. After 20 days, it gives a count rate of, so we have the count rate of 500 counts per minute. What is the half-life of the material? So this is 20 what? So 20 days. So we have 20 days there. Now, if we have 20 days, so this 20 days it carried it to, or it carried it this far. So now, what is the half-life of the material? So we want to look at the half-life of the material in what? In days now. So meaning that we have, this is, okay, we say this is the 1, and then we say 2, then we say 3, we say this is 1, and then this is 2, and then this is 3, and then this is 4, and then we have the 5 there. So that is the half-life of the material, which is so the answer here it is B, which is 5. So let us move. So we can move. Let's move to section B. So section B. So section B answer all questions. So this section carries 45 marks. So figure B1.1 below shows a simple pendulum suspended from a fixed point. So we have a simple pendulum. So this is a simple pendulum. So now we have A, B, and then we have a string, and then we have a bob there, and then we have a fixed point. And then, so we have, the first question is, the bob is slightly pushed to position A and then released. So it was, so from A it was pushed, so it was pushed. So after it was pushed, so we can say state one factor that does not affect the period of the pendulum. So we want to look at the period of the pendulum. So we want to look at the period of the pendulum. So now we are looking at what will not affect. So we can say, for us to understand this, first of all, what we should know is, if it was pushed, again, this bob will come back to what? To A. So when it comes back to A, so that is one oscillation there. So now state one factor that does not affect the period of the pendulum. So we have number one, the mass. We can say the mass of the bob. So the mass of the bob. Okay, so let us move to, so if the value of time, if the values of time for 20 oscillations obtained were, so we have 16.1 seconds, 15.9 seconds, 16 and then 16.2 seconds, and then we have 15.8. Calculate the period of the pendulum. So meaning that I stated earlier to say for one oscillation, meaning that the bulb should go and come back on the same position, which is A. So we'll count that to be one oscillation. So now for us to find the period of the pendulum, first of all we have to find the time average. So time average. So would say 16.1 plus 15.9 plus 16 plus 16.2 plus 15.8 over what do we have? 1, 2, 3, 4, 5. So over 5. And then when you add them and then you divide by 5, what are we going to have? So we're going to have 16.0. So this is the time average. So now let us find what we are looking at. So we are saying that for us to find the time is equal to, so we have time average over n. So time average, which is the oscillation there. So we are going to say is equal to, so we're going to substitute. So we have 16 over the oscillation, so 20. So when you divide on your calculator, it will give us 0.8 seconds. So that is the time. So 0.8 seconds. So calculate the frequency of the pendulum. So we want to calculate the frequency of the pendulum. So how do we calculate the frequency of the pendulum? So we would say frequency is equal to 1 over t, and then so this is the period. So time, or t, is the period. So in this case we would say frequency is equal to, so 1 over 0.8, because we calculated this earlier. So we're going to say it is 1.25, and then it is in Hertz. So those are the units that you have to use. So here it is 1.25 Hertz. Okay, we move to B2. A car has a mass of 900 kg. It accelerates from rest at a rate of 1.2 meter squared per second squared. Sorry. So calculate the time taken to reach a velocity of 30 meter per square. So here we want to find the velocity. So the formula that we're going to use, because we have, number one, what we have to understand is we have this. So this is the mass of the car, and then we've been given the acceleration there to be this. So we want to find what? The velocity. Now, how do we find the velocity? So we would say acceleration is equal to velocity over initial minus initial over the time. So we would say the velocity that we've been given, it is what? The velocity. So the velocity is 30. So we write 30 minus the initial, the starting point. So the starting point, meaning that it accelerates from rest. So when we say accelerate from rest, it means that it is 0 over time taken. So time taken is not known. That is what we are looking for. So therefore we say acceleration, so 1.2 is equal to 30 minus 0 over t. So you can cross multiply here, So we're going to have 1.2t is equal to 30. So because we want t to be solved, therefore we're going to divide 1.2, and here we're going to write 1.2. So 1.2 goes, so we have t is equal to, so 1.2 into 30. So 1.2 into 30, we're going to have 25. So we're going to have 25 seconds. So the answer is 25 seconds. So force required to accelerate the car at the rate of 1.2 meter per second squared. So we want to find the force. So we want to find the force. So we'd say force is equal to mass times acceleration. So force is equal to mass. We've been given mass. So mass we've been given. So mass we've been given, which is what? Which is 900 kg there. So we've been given 900 kg. So we'd say 900 times we've been given the acceleration, which is 1.2. So force is equal to, when we multiply, we'll find that we're going to have 1018. The units for force, we have newtons there. So we can write 108. Okay, so and then okay, so we have 101, and then we have 8. Okay, we can move. Okay, so we have figure 3.1 below is a diagram showing a load being moved using a wheelbarrow. So we have a wheelbarrow, and then we have load here, and then we have the handle, and then the force, and then we have the weight of the load. So we have the weight of the load, and then we have the distance here. So now the question is the total mass of the wheelbarrow, and the load is 80 kg. So take G as, so we've been given G, we've been given to be 10. So now here we want to look at the first one. So calculate, so weight of a wheelbarrow and the load. So we want to calculate the weight of the wheelbarrow. So we'll say weight of the wheelbarrow is equal to mass times the G there. So we would say weight is equal to, so we've been given which is the mass, which is here. So we have the mass. So the mass we have there, which is 80 times, so we have there we have a 10. So when we multiply, 80 times 10, we're going to have 800 newtons there. So we have 800 newtons. So excuse me, so force F required to lift a wheelbarrow. So we want to find the force which is required to lift the wheelbarrow. This force to lift what? The wheelbarrow. That is what we want to find. So which is needed for a wheelbarrow to be lifted. So we would say, so we are going to say F times, so distance 1 is equal to, so weight times distance 2. So when we look at the wheelbarrow very closely and very carefully, you'll find that there are certain things that we have to understand. So There are certain things that we have to understand here. So we have the distance. So the distance that we have, so distance 1, so we can say distance 1 that we have, it is from here up to there. So this is distance 1. So when you add the distance which has been given, so we have 1.5 and then we have 0.5. So here it is 10, here it is what? Here it is 2. So we have 2. So here it is 2 meters. So that is the distance for distance 1. And then distance 2, it is this one which is here. This is the distance 2 that we want, and then this is D1. Okay, so we can move and answer the question. Okay, so which was being lifted. So the force here, so the force, because this is what we want, and then so we would say F times 2 is equal to this. We've calculated W, we've calculated it before. So we've calculated before, so the weight is 800. So we have the weight which is 800. So we'll say 800 times 0.5. And then we'll say 2F is equal to, when we multiply 800 by 0.4, so 0.5, so we're going to have 400. So we're going to have a 400 there. So because we are solving for F, so we introduce a 2 there, and then we introduce a 2, so that 2F so is equal to, so 1 here it is 2, so we're going to have 200 newtons there. So the answer is 200 newtons. So we can move. So state whether force F would increase or reduce when the handles of the wheelbarrow are made longer. So we want to know if the force would increase or reduce if we were to increase the handle of a wheelbarrow. So if we are to increase this, does it mean this force will do what? It will change, it will increase, or it will do what? It will decrease. So we want to state whether it will increase or what? Or reduce. So we would say the force, so there will be that change. So the force would be reduced. Or we can say it will decrease, or it will decrease. Okay, we can move. Okay, so figure 4 B4.1 below is a diagram showing a stone of mass. So we have 2 kg that was pushed up a slope from Q to R. So we have this is the ground. So this was pushed to, so the stone was pushed. It started from Q and then it was pushed to R. And then we have S, which is the midpoint, and then we have T. Okay, so we can say 72 joules of work was done in moving the stone up and the slope from Q to R. So what is the potential energy of the stone at R? So we want to see the potential. What is the potential energy of the stone at R? So the potential at R, so this is where R is. So now you'll find that to find this, it is very simple. So now, because they've given us something, or they've given us some information to say 72 joules of work. So this 72 joules of what? Work was used to push the stone up to the top. So now, because here they used energy, so that energy is what we're going to say the potential energy it possesses is the same work which was given here, which is 72 joules of work. So we can say 72, that is the potential energy. So we can see P is 72. If the stone falls through side RT, what would its potential energy be at S, the midpoint of its fall? So we are looking at if the stone falls through side D, so we have side D, so R and T, so this is the midpoint. Okay, so the midpoint. So how do we find the potential energy? How do we find the potential energy? So we are saying that potential energy is equal to half, because that is the midpoint. So we're going to use half. So times, which is 72. So 72, that is the work. So the work, which is 72. So here is equal to, so it will be 72 over 2. So 2 into 7. So 2 into 7, it is 3, remainder 1. So 2 into 12, it is 6. So that is the answer, which is 36 joule. So 36 joules. So 36 joules. So we are saying that this is 36 joules. Okay. So calculate we have the height RT. So we want to calculate the height, which is RT, this height. So that is what we want to calculate, the height. So we want to calculate the height. So how do we find and how do we calculate the height? So we would say in the formula for potential energy, we will find height. So we would say P, which is potential energy, is equal to, so we have this formula. So we are looking at the height because we have the height there. So let us look at, and we make H the subject of the formula. We can make the subject of the formula, which is H, to be the subject of the formula. So if we make H the subject of the formula, we're going to introduce this, and then it will be like this. So this will go, so H is equal to, so PE over, so that is the formula, that this is the formula that we're going to use. So we say, so we can substitute now. We can substitute. So we are saying that this is the potential energy. It is 36, and then we have 2. Where is this 2 coming from? Where is this 2 coming from? So where is that 2 coming from? So this is the mass that we have here. So this is the mass that we have there, which is a 2. And then, so we have times 10. So where is this 10 coming from? Where is this 10 coming from? So we're given a 10. So we are given Okay, so this is it, because we're looking at the 4 here, so this is the gravitational force, so which is 10. So we're going to have 36 over 20. So it will give us 20 into 36. So 20 into 36, we're going to have 1.8 meters. So that is 1.8 meters. Velocity of the stone just before it strikes the ground. So before it strikes the ground. So before it strikes the ground, that is what we want to look at, the velocity. So we would say quickly, without wasting time, so we would say velocity, we're going to square it. So 2, this is the gravitational force, and then we have the height there. So we would say V, okay, so 2 times, we have 10 times, we have, right, so 3.6. Now where is this 3.6 coming from? So where is this 3.6 coming from? So let us look at very closely. 3.6 coming from, so we have, this is the meter. Okay, so this is the area that we are looking at. So now we want to see how it was falling. So we would say we've been given, so this is the height that we want. So because before it's 4, so we would say 1.8 plus 1.8. So what are we going to have? So 8 plus 8 is 16. Then 1 plus 1, it is 2, and then plus 1, which is 3. So that is 3.6. That is where it is coming from. So that is before it's 4. So that is before it's 4. So when we calculate on the calculator, you'll find that we're going to have, so this is 20. So 20 by 3.6, so we're going to have 70. So this is, we're going to have 72 here, and then let us find the square root for 72. So we have 80. So we have 8.485228. So initially we can write it 8.5. So that is the velocity, which is 80.5 meter per watt per second. Don't forget the units there. Don't forget the units. So let us move to 5. Okay, so below is a diagram showing a wave traveling along a spring in the direction shown. So this is the direction. So we've seen the direction where it was going. So we have the wave direction, and then we have U. So this is where we find U. So this is where we find U. And then we have, so even here it is one and the same. So this U, we are saying that this can be U, and then even here can be U, and then we have W, then we have W, and then we have W there. So in what way is this wave the same as a sound wave? So we want to know in which way this wave is as the same as the sound wave. So the sound wave, we say that the sound wave moves in a longitudinal, or that is a longitudinal wave. So even this one, we can see it to be, this is a longitudinal wave still. So we can say that the string vibrates. So the string vibrates parallel. So parallel to the direction of travel of the wave which is similar to the vibration of particles in sound wave. So this is the answer. So what are regions U and W? So the region that we identify, so this region which is U and W. So we are saying that this region which is U, it is called, or it is known as the compression. So this is the compression. So this is the compression, and then this is the compression, this is the compression as well. And then W, so W it is, so we have rarefaction. So rarefactions, so that is here and there as well. So explain why sound wave travel faster in liquids than in gases. So we want to explain why this it moves faster in liquid than what? Okay, so we can say that the particles, so the particles are much closer in liquids, and so they can quickly transmit, so they can quickly transmit, so transmits vibration energy from one particle to the next particle. So that is the answer. Let us move to question 6. So question 6, so we are saying that B6, so a ray of light travels from air into water at an angle of 40 degrees between the normal and the incident ray. If this ray produces an angle of refraction of 29 degrees, calculate the refractive index of water. So we are saying that we are looking at, so this is, so refraction, we say it is the bending of what? So it is the bending of light. So this is what we are talking about. So this is what we want to look and to talk about. So we can say, how do we calculate this? How do we calculate this? How do we find the refractive index in water? So we would say refractive index is equal to, so sine, so this is the incidence over the sine, which is the refractive. Then so it will give us, so we've been given, so we have the first one we've been given, which is the, so a ray of light travels from air into water at an angle. So meaning that we have the first one, which is here, which is 40. And then here we've been given, which is what? 29. So it was closer to the line which divides. And then so here we're going to substitute to say, so we have 40 over, we have 29 there. So when we use our calculator, we find that we're going to have 1.3. so that is the refractive index, it was 1.3. So we can move to the critical angle of water. So the critical angle, so we would say the critical angle is equal to, so sine inverse, and then in bracket 1 over the what? The refractive index. So here we would say sine inverse, and then 1 over the refractive index that we calculated, which is 1.3. So when we use the calculator, you'll find that it will give us 50 degrees. So that is 50. So 50 degrees, that is the critical angle. So we can move this. So the diagram below, the diagram showing we have 240. So this is 240 volts main supply connected to a television set, a television and 2 lamps. So we have, this is the television set here. So this is the television set, and then we have, these are lamps. So we can say the first one calculate total power supply. So we want to calculate the total power supply. So we would say power supply is equal to, so the power supply that we have here, the power supply that we have, so we would say 120 watts plus, which is this 40 plus that 40, we're going to have a power supply. So we would say 120 plus 80. So it will give us 120 plus 80. So we're going to have a 200 watts. So meaning that that is the power which was supplied. So we have, that is the power. And then total number of kilowatts hours of energy supplied to circuit in 3 hours. So we want to see. So we would say, because the total number of kilowatts supplied of energy in supplied to circuit, which is in 3 hours. So what are we looking for? So we want to find the energy here. So the energy, we say energy is equal to, so P power times what? Time. So we'd say P we've calculated, which is 200. So 200 times the time that we've been given, that is 3 hours. So we'll say 3 hours. So therefore, when you multiply, we're going to have 600. So this 600 that we have, now we've been asked to say the total number of kilowatts. So meaning that, so kilowatts. So this, we're going to divide the answer that we've given by with 1000. So this 1000, so 0, 0, 0, 0. So 10 into 0.6, so we're going to have a 0.6 kilowatts per hour. So we have kilowatts per hour. So 0.6, then we have kilowatts per hour. And then we have the potential difference across the television set. So the potential difference across the television set. So when you look at the potential difference, so the potential difference, it is the same in the parallel, because we have, this is what we are looking at. So this is what we are looking at. So the potential difference. So you find that because we are looking at the potential difference, the voltage is the same in parallel. So the voltage is the same in what? In parallel. So we'll just go direct to say the answer is 240. So 240, and then we can say, so voltage in parallel is the same. Okay, so we have come to this is a diagram showing a coil of wire wood on a soft iron core, so with the current flowing in the direction indicated by the arrows. So we have X and we have Y there. So now this is the soft core, and then we have these are wires, and then the current was flowing in this direction. So we want to understand and to know. So mark the north and the south pole induced on the iron core. So now how can we know the side, the north pole and the south pole? So we're going to use a thumb that will determine the flow of what? The flow of current. So you'll find that the flow of current will be flowing in this direction. So we have the flow of current, so will be moving in this direction. So you'll find that the thumb will be like where the thumb will point. So this is the thumb, and then we have these are fingers. So where they are pointing, this is the flow. So the flow of what? Of current. So the flow of current, and then where the thumb is pointing, that is the north pole. So we would say here we have the north pole, and then here we have the south pole there. Then what else? What else are we looking at here? What else? So what else? So we are saying that show by an arrow the direction in which a plotting compass needle would point when placed at X. So if a compass needle was placed at X, where can it point? So an arrow so looks like this. So here this is the north. So where will it point? So where will it point? So where will it point? So you find that because of the flow of current here, and then the current will be moving in this direction. So the current will be moving like this. So meaning that the hand that we used will help us to find the flow of current, and then the needle. So the needle will point in the direction of what? The direction of current. So let's say, so the needle will point in this direction. Okay, so at X, so we have at X. So because we are looking at x there, so we say point in this direction. Okay. So a beam of electron flow through points y in the direction perpendicular downwards into the paper. Show clearly using an arrow labeled F and the direction of the force exerted by the magnetic field on the electron beam. So we want to know exactly where. So you'd find that in this, to answer this question, you can use the Fleming right-hand rule. So it will help us to find where the position or the direction of this what we're talking about. So you find that this the hand rule, so would say, so we have a thumb there, then okay, so here, so would say this is motion, and then here would say this is the magnetic field, and then here would say this is what the current. So now when this is moved, you'd find that this will do what? It will move, the hand will be moved in this direction. So when the hand is moved in this direction, you'd find that the position and the flow of current will do what? Will change depending on where this will point, or the middle finger where it will do what? It will point. So this is the magnetic field. So the magnetic field where it will do what? It will point. So you'd find that here it is. So show clearly using the arrow labeled F. So the arrow labeled what? F. So the arrow labeled F. So we find that it will move. So we would say it will move. So we would say F, it will move. This is upwards. Okay, so we can move. Phosphorus, so we have phosphorus, which is 32, and then can decay by emitting beta particles. So what is a beta particle? So we can say, what is a beta particle? So we are saying that it is a fast moving electron. So that is the simplest definition that we can find. So when we look at if the proton number of phosphorus, which is 32, is 15, so state the new value of protons and mass number of the inclined just after it emits a beta what? A beta particle. So we have the proton number. So the proton number, we want to know the proton number. So the proton number will be because it will change. So let me explain something here. So meaning that if we have, so we have A and then we have Z, then let us say, okay, we say we use X. Okay, let us use X. Okay, so we're going to use X. So we'll say X, then we have A, and then we have Z. So meaning that what we're going to have here is, number one, we're going to have when it undergoes a decay, you find that we're going to have a new substance after it has lost one, so we can say 1 electron. So once it has lost 1 electron, so we're going to have a new, meaning that here the the proton number will do what? It will change. So the proton number, it will do what? It will change. Meaning we're going to move. So on the periodic table, it will move one step what? Forward. So it will move one step forward. So meaning that we're going to have a 15 plus 1, which is 16. So here we're going to have the proton number, which is 16. And then the mass number will not what? The mass number will not change. It will remain with 32. So write the decay equation for P, which is 32 after emitting 2 beta particles. So after emitting 2 beta particles, so we'll say P, which is 32, and then we'll say 15, that is the proton number. So it will undergo, so meaning that 32 will remain, and then here we're going to have 17. Why if we say 17? Because of what? 2 beta particles. So 2 beta particles. So we'll say 2, which is 2 beta particles. So we'll say, so this is 1. So 1 times 2, we're going to have a 2. So this is the equation of decay that we were asked to find. So C, we have C. Phosphorus, which is 32, can be used to prove the plant absorb phosphorus nutrients from the soil around them. State 1 safety precaution which should be taken into consideration when doing experiments with phosphorus 32. So we'd say, what are you supposed to do? So they've asked us to say what are the precautions so that you have to consider. So we just state 1 because we've been asked 1 precaution. So the first precaution that we're going to write is you should protect yourself. So you wear radioactivity, so radioactivity protective gloves. So radioactivity, we say radioactive protective, so protective gloves or gears. Okay, so we end here. Thanks for watching. So you can subscribe and share the video.